A very good day to Dr. West. So, today I'll be presenting my individual assignment for CHM3342, Organo Transition Metal Chemistry. So, before I'll start with my presentation, I would like to introduce myself. My name is Lim Wai Lun. My check number is S70917. My lecturer for this course is Dr. Uwais Sukani. And the title that I picked is Pyridine 2 Olato Bridge, Dirodium 2, Dirodium 3 Acyl Organometallics, Synthesis, Spectroscopic, Structural, and Theoretical Studies. So, after the introduction, I would like to show the structure for the organometallic complex from the title just now, the article from Science Direct. And as you can see, there is a central metal ion in the center of the complex, where the metal can be either rhodium or technetium, which is also known as Re or Tc. There are also two compounds present in the journal, in the article, which are the left side and also the right side ones. So now we'll move on for the naming for the organic metallic complexes. So we'll start with the left side one. The left side has several ligands, including pyrimidine 4,6-dicarboxylic acid, which is also known as HPMDC. This is because the the reason why it is 4,6 is because the end at the bottom starts with 1, and then it starts by going to the right side, anti-clockwise. So it will be 1, 2, 3, 4, which is the carboxylic acid functional group, and then 5 as well as 6, the bottom one, another carboxylic functional group, which is why there is 4 and 6 dicarboxylic acid functional ligands. All right. So other than that, there are also 3 carbonyl ligands that are linked they are bonded to the center metal ion, the amp, as well as one aqua ligand, H2O. There is a last one bonded to the center metal ion, center metal complex. Okay. So on the other hand, the oxidation state for the carbonyl ligands will be 0. The water molecule is also 0, which, as you can see in the oxidation state, there will be 0 times 3 carbonyl ligands and 0 times water ligands, which is known as aqua. So the oxidation state for HPMDC will be -1. So when you go down, it will become N plus 0 plus 0 plus -1. So the oxidation state for the center metal ion will be +1 to neutralize the -1 charge from the pyrimidine 4,6-dicarboxylic acid, HPMDC. All right, as a result, in the end, the naming of an organometallic complex with including the metal ion for when the metal is rhodium, it is named as aqua tricarbonyl pyrimidine 4,6-dicarboxylic acid rhodium 1. When the metal ion is technetium, it will become aqua tricarbonyl pyrimidine 4,6-dicarboxylic acid technetium 1. On the other hand, the naming for the right side complex earlier, it has a ligand of pyrimidine 4,4,6, but the 4 is still remain as carboxylic acid, and the 6 will be changed from carboxylic acid into a methyl ethyl ketone, which is also known as a 1-butanol. But since it's in inorganic chemistry, it's in organometallic chemistry, so we will change it to methyl ethyl ketone, which we know the whole ligand as HPMDC. Therefore, there is also similarly 3 carbonyl ligands bonded to the center metal ion and 1 aqua ligand H2O bonded to the center metal ion. On the other hand, the oxidation state remains the same, where there are 3 times 0 carbonyl ligands charge, 0 times 0 for the H2O is 0 charge. So yeah, 0 times 1, it will be also remain as 1. However, the HPMDC will still remain as -1. So when m plus 0 plus 0 plus -1, you get m equal to +1 to neutralize the -1 charge. Hence, the oxidation state for the center metal ion in the left side, in the right side complex for this complex on the slide will be +1. On the other hand, for naming for the second one will be if the metal is rhodium, it will become aqua tricarbonyl pyrimidine 4-carboxylic acid 6-methyl ethyl ketone rhodium 1. And if the metal is technetium, it will also become aqua tricarbonyl pyrimidine 4-carboxylic acid 6-methyl ethyl ketone technetium 1. So now we will be discussing the synthesis method for all the metal complexes, So for the left one, the ones with dicarboxylic acid, aqua dicarbonyl pyrimidine 4,6 dicarboxylic acid, rhodium or even technetium. We'll start off by using the pentacarbonyl, bromopentacarbonyl rhodium, and also the pyrimidine 4,6-dicarboxylic acid. They are both dissolved in the distilled water first. After that, the dissolved mixtures will be placed into a setup apparatus consisting of the round bottom flask and also the condenser. And the water is connected to the condenser to allow the reflux to take place. And they will be dissolved inside the two-neck round bottom flask and heated as well, and constantly stirring by using magnetic stirrer for 6 hours. After 6 hours, a yellowish orange precipitate will be formed at the end of the reflux, and the product will be directly filtered after the solution is cooled to room temperature. And therefore, the observations will be there are no precipitate obtained during the filtration process, which is on the filter paper. So the whole products they will be dissolved in the solution and dissolved through the filter paper. All right. Okay, so after the filtration, the yellowish orange precipitate solution will be reduced to 5 ml by constant stirring using magnetic stirrer, which promotes evaporation of the water of the solvent into the atmosphere. Therefore, we only take the 5 ml of the solution and allow it to dry by covering with a parafilm and then put it on the shelf overnight. After that, we will do purification by washing the precipitate by using DCM dichloromethane and also diethyl ether. After washing process, we will do double washing so that we will improve the purity of the product, and therefore we will also dry in the vacuum desiccator for 5 to 6 hours in order to remove the water contaminants that are present in the complex compound. On the other hand, for the synthesis for second one, the aqua tricarbonyl pyrimidine 4 carboxylic acid 6-methyl ethyl ketone radium or even technetium, we will use either radium or technetium the metal compound, which is a bromopenta radium 1 or bromopenta technetium 1 compound, and also pyrimidine 4 carboxylic acid 6-methyl ethyl ketone HPLDC. They are both, as well as butanol. We will all dissolve them in the ethanol instead of distilled water because they are all soluble in ethanol. Hence, all the compounds will be placed in a 2-neck-round proton flask similarly like the previous one, and we will conduct reflux process for 6 hours for them to mix together to form the desired product. And at the end of the reflux, we will get a orange precipitate and orange color precipitate, and the product is filtered after cooling to room temperature. As similarly, there are no precipitates that are insoluble in the ethanol. Hence, everything will appear as a filtrate after the filtration process. After the filtration process, we will also reduce the solvent to 5 ml, the solution to 5 ml by constant stirring by using magnetic stirrer, which promotes evaporation. After that, we will rub up using a parafilm and put it on the shelf overnight to promote evaporation. So on the next day, we'll do further purifications as well, but we will wash the precipitate by using ethanol instead of TCM because they are soluble in ethanol. Hence, we will use ethanol and ethyl ether for the washing process. And then after that, after washing, we will dry in the vacuum desiccator in order to remove the water contaminants that are present in the precipitate or even the complex compound. Okay, so now we will proceed with the reaction times of the metal complex that they will undergo. So one of them will be ligand substitution reaction. This is because we can see that the bromine ligand is replaced by HPMDC as shown on the slide. So the bromine will be replaced, and meanwhile the three carbonyl core will remain instant, suggesting the stability of them connecting to the center metal ion. Okay. On the other hand, the other reaction types are also chelation reaction and also thermal assisted completion. So chelation reaction is because of the ligand of HPNDC of multiple donor atoms. They consist of a lot of donor atoms such as oxygen and nitrogen, which allows the formation of chelate rings with metal. So we form metal carbon bonding, which is which is the most important bonding in organometallic complex. Other than that, the thermal assisted convection requires heating. It's because the reflux requires heating to drive the reaction to start the reaction. So the main reason why heat is required because the kinetic energy is required to break the energy barrier, the ligand barrier for ligand exchange or ligand substitution. For example, for TC complex, you must require at least 80 degrees Celsius to break the ligand bonding for ligand substitution or even the substitution process to take place. All right, so now I'll be presenting the applications for technetium complex, which is also known as TE. So, the main isotope they will use for technetium applications will be technetium 99M, which is also known as TE99M. It is commonly used by doctors for medical specific medical scans, which they call as SPECT, SPECT imaging. So the cool thing is that scientists can tweak certain chemicals so that the chemicals they will stick to particle things or molecules such as sugar, peptides, protein peptides, medicines, or even antibiotics to the part of our cells. So this helps to guide the scanning process, right where they want to look inside the body for the checking process. Because of this, technetium-99m is a super versatile, super useful finding for cancer spots or cancer cells in our body, checking how our heart works, and also spotting problems in our bones, such as breakings or infections. So basically, it is a handy tool for doctors to see what is going on inside our body as a patient. Okay. Okay. Last but not least, I will be presenting the applications for rhenium complex (RE). So the use of rhenium complexes, we will normally only use non-radioactive rheniums that help scientists to study how cancer-fighting drug works and to move throughout the body. So it acts like a practice version before using a real treatment. Secondly, radioactive rhenium sends out healing energy particles into our body, which is also called as beta radiation. That its target will destroy the problem areas or the target cells, such as cancer cells. Okay, so doctors will use these to treat liver tumors, relieve bone pain in cancer patients, as well as combine with special dyes so that they can see exactly where does the treatment working inside the body. Okay, it will help both treating and tracking disease at the same time. So pretty much that's all for the applications for radio. So that sums up the presentation for this video. All right, so thank you, doctor, for the time and energy to watch this video, and I hope you have a good day.